Coming to next topic, transmission of power in rectangular waveguide. Now power transmitted through the waveguide and power losses, both transmission of power and power losses both are calculated using the Poynting theorem. Now you know the Poynting theorem, power transmission and the power loss can be calculated by using Poynting theorem. Now that is given by integral P dot ds. Now P, we know that half of E cross H. Now expanding that, you'll get this equation. Now generally a waveguide, a rectangular waveguide is filled with air. Now for a lossless dielectric, the time average power, right? For a lossless dielectric, the time average power is given by this equation. You can take half out, that is half of Z to Z, which is nothing but wave impedance, integral E cross H, we can write it as with respect to electric field, mod of E square into d, right? Now power transmission and power loss both are calculated by using the Poynting theorem. You know the Poynting theorem, that is E cross H. Now for a time average is given by this equation. Now we know, coming to next one, now we know Z to Z is nothing but wave impedance, that is electric field strength in one transverse direction to the magnetic field strength in other opposite direction. Now that is E square is given by Ex square plus Ey square, and similarly H square is given by this equation. Now the average power transmitted through the rectangular waveguide of dimensions A and B, using the dimensions A and B, is given by this equation. See, rectangular waveguide supports both TE mode and TM mode. Now we have to calculate transmission of power for TE mode and TM mode. Now coming to for TE mode, now we had derived this expression in previous lecture, that is wave impedance of TE phase, that is neta by under root of this equation in terms of cutoff frequency and in terms of cutoff wavelength, right? Now in terms of Z, to suffix Z we have to substitute this equation, right? We have to substitute this equation, and E square is nothing but Ex square plus Ey square with respect to dimensions A and B, and A is with respect to x-axis, that's why dx, and B is with respect to y-axis, that's why dy. You'll get this equation. Finally, substituting wave impedance, and E square is nothing but Ex square plus Ey square, and along x-axis you will have A term, that is 0 to A with respect to dx, and along y-axis 0 to B with respect to dy. And in terms of lambda, this is the equation. Only in terms, this will vary, right? And this expression is in terms of cutoff frequency, and this expression is in terms of cutoff wave. Now similarly for TM mode, you know this expression, right? Neta into under root of Fc by, substitute in terms of wave impedance, substitute this equation, and this is transmission of power in TM mode with in terms of cutoff frequency, and transmission of power in TM mode, transmission of power of TM mode in terms of cutoff wave. Now these are the formulas for transmission of power in TM mode and TE mode, which are based on the wave impedance. Now coming to next topic, that is power losses in a waveguide. The losses in a waveguide can be due to two cases: attenuation below cutoff frequency and dissipation within the waveguide walls, right? See, in a waveguide, loss when F is less than Fc, you will get, when signal frequency is less than Fc, signal gets attenuated. There you will get power loss, and another one is dissipation within the waveguide. These two cases, in these two cases, power losses occurs in the waveguide. Now we know that lambda g equals to 2 pi by beta, and beta, from this expression you know that 2 pi by lambda g. Now beta becomes imaginary, implying wave attenuation. When beta is real, which indicates wave is allowed through the waveguide. When beta is imaginary, which indicates wave is attenuated. Now we have to you know the lambda g expression. First calculate beta, right? Now 2 pi by lambda g, substitute lambda g value in terms of cutoff frequency. See, this lambda g is this expression. Now beta is nothing but 2 pi by lambda g. Substituting this, you will get this equation, right? Now from this expression, take Fc by F out, you will get this one. Now Fc by F by lambda is nothing but lambda equals to C by F. Now F by lambda is nothing but C. Now this you will get this equation, 2 pi Fc under root of F by Fc square minus 1 by C, right? Now coming to this one, now 2 pi into under root of F by Fc square minus 1. See, here you have Fc by C, right? Here you have Fc by C, I can write it as lambda C. Fc by C, I can write it as lambda C. Now totally you will get beta equals to 2 pi under root of f by fc square minus 1 by lambda. Now I said beta becomes imaginary when wave gets attenuated. Now this is the expression when wave is getting attenuated, and the amount of attenuation is given by 2 pi by lambda c into under root of 1 minus f by fc square dB per length, right? And hence the cutoff attenuation constant, right? From this expression only you will get this. Only this constant will vary, except that everything is same. 54.6 lambda c divided by under root of 1 minus f by fc square dB per length. Now for f greater than fc, waveguide exhibits very low loss, and for f less than fc, attenuation is high. This is about the power loss in the waveguide. Now when the waveguide is filled with dielectric, now this is the formula for, you just remember this formula. Now this is the formula when the waveguide is filled with dielectric medium, and this is when the waveguide is filled with air, right? You only this constant will vary, except that everything is same, right? Now coming to next one. Now from this expression tan, you have tan this thing, right? Now this is nothing but dielectric loss tangent of insulating material, right? No need, just remember the formulas, right? Now coming to next one, breakdown power in the rectangular waveguide. Now you know the dominant mode of rectangular waveguide is TE10 mode. Now this is the formula for breakdown power in rectangular waveguide. Just remember formulas, no need of derivation. Now coming to next one, power handling capacity of rectangular waveguide, and this is also, and these two are for air filled waveguide. If it is filled with dielectric, that is different. Now these two are for air filled waveguide, and this is for formula for power handling capacity of rectangular waveguide. And for standard rectangular waveguide, that is B equals to half, right? Now coming to this expansions, where ED is the dielectric through of dielectric strength of the insulating material in the waveguide, and F is the operating frequency, Fc is the cutoff frequency of dominant mode, and F max is the maximum frequency in megahertz. And this is the concept of power in rectangular waveguide, and here ends the topic of rectangular waveguide. In the next class I will start circular waveguide. Okay, thank you.